Okay, so this tutorial today is all about using two different types of data structures in MATLAB. They are what are called structured arrays and cell arrays. Now, you probably haven't used them before in MATLAB, but they're really useful. I'm going to set up a simple example to show you how they work, and then we're actually going to do that problem on the homework where you had to do this for many different values of the eccentricity, and we're going to actually code the differential equations, and I'm going to show you how you can organize information using structures so that we can actually make this code a lot more compact, a lot more readable, and actually a lot more accessible and useful, rather than having data all over the place and not being able to organize it well. So the first thing I'm going to talk about are what are called structured arrays. And the easiest way to do this is using the following example. I've used it several times before. So let's think a little bit about how you organize information in something that you use on a daily basis. Something we all use on a daily basis to one extent or another is a calendar, right? We all work with calendars. We all have appointments. We all have things that we need to do during the day, and somehow we organize all that information. I have a doctor's appointment. I have class. I have a meeting. I have something else, right? So in its essence, when you organize information in a calendar, you have three things that you normally need to work with. You have a date, you have a time, and you have an event. Right? Those are the three key things that you have in every entry in a calendar. You may have other things too, but those three things are the key things that you have. Now, every single entry in the calendar is going to have a date, a time, and an event. Now, if you're going to organize information in a calendar, how would you do it? Well, working with a numerical array, which only holds numbers, isn't going to help you, because a date, a time, and an event are not easily describable by numbers. Certainly an event is not describable by numbers, right? It's usually a string, something that you have in words, right? So to put that in a numeric array isn't a very easy thing to do. It's a very difficult thing to do. So what you can do is you can create what's called a structured array. Structured arrays work like this. They're not hard to work with, but you have to understand how they work. They work with what are called fields, and every entry in the structured array has fields. So rather than be abstract about this, let's actually set this up with a calendar. So let's suppose I have my calendar. This is a made up problem, right? And I'm going to say calendar of 1. Calendar of 1 is the first entry in my calendar. That's all it is. And everything that's in this entry is going to be associated with that particular with this particular number 1 in the calendar. Now, if I look at this, say, well, what do I have? I've got a date. So let's say the date is today. It's 11 September 2020. Now that's a string that gives me the date. The second thing I would have in a calendar is I would have a time. So calendar of 1.time. And let's suppose I say, 3 p.m. Okay? The third thing I'd have in a calendar is going to be the actual event. What is this thing that I'm actually going to be doing at 3 p.m. on the 11th of September today? Well, I'll say, okay, I'm going to go shopping, right? So this is just something that I'm like I said, I'm making up. Now, if I look at calendar, it says that it's a struct. A struct is exactly that. It's a structured array, and it has three fields: date, time, and event. Now, if I'm going to create a second entry in the calendar, so let's suppose tomorrow I'm going to go have lunch with somebody, right? So, and I'm going to say, well, this is going to happen on the 12th of September. So now this is my second entry in my calendar, and it's going to be .date, and that's going to be 12 September 2020. And then I say calendar of 2.time. Well, people often have lunch around noon, so I say 12 p.m., right? And then calendar of 2 .event is going to be lunch. I'll say lunch with mom. Okay? Now, look at calendar now. You see that it's a 1x2 struct, right? If I access calendar of 1, it gives me the following result. It gives me three fields, date, time, and event, with those particular values for date, time, and event. If I look at calendar of 2, look what happens. It gives me the information on the entry, the second entry, which is tomorrow at noon, right? So you can see that by accessing the calendar in this particular way, I can organize information by name. Do you see? It's because the fields that are in each entry in this structured array are the same. Calendar of 1 contains 3 fields, date, time, and event. Calendar of 2 also contains 3 fields, date, time, and event. And every entry in the calendar will contain that same information. So if I add another entry into the calendar, the structure is designed in such a way that you should have those fields in every single entry in your calendar. And that gives you a way to be able to organize information in a way different from dealing with numbers. You can see that by looking at this information is not easily organized in a regular numeric array. That's a very difficult thing to do with a numeric array. The other thing is that the names, date, time, and event, provide me a way to be able to work with information that I would normally associate with a name rather than a number. So let's think about this in the context of an array. If I have an array, and let's suppose I could organize this information in an array, then what I would have to do is I would have to look it up by number, right? I have to look it up by row, column, index, like IJ, right? I'd have to look at what the third row, second column is. But then I'd have to remember what the first column of information contains and what the second column of information contains. I'd have to keep track of that myself because I'm indexing into an array with numbers. Here I'm not indexing into an array with numbers. I'm indexing into an array that each entry contains fields, and those fields have names, and those names are names that I've given those fields. So those names should have some meaning to me, right? So I'm looking at this and saying, well, I'm going to do this in such a way that date means something to me. When I see calendar of 1.date, that should give me back a date, right? It should give me back something that corresponds to some day on the calendar, right? Similarly, the time should be something that's meaningful. If I say 3 p.m. for the time, that's meaningful. If I put something in that field time that isn't meaningful, it's going to be, I'm going to look at it and say, well, that's not a time. If I put, calendar of 1.time and I say like, I put something that's completely irrelevant to what a time would be, that wouldn't make any sense for that entry. But I know that time as the field means that what I should be seeing when I access that is going to be something that's going to be a time. So look at this. If I say calendar of 1.event, it gives me shopping. If I do calendar of 2.event, it gives me lunch with mom. Now, this is absolutely the key thing about a structure, is that you see that there? That is an actual period. That's the period. It is a structured array. It's an array of structures. Structures are delimited by a period. Now, the thing about this is that you can have structures of structures. You can say each one of these structures could itself actually be a structure. And then you can be recursive, where you have structures of structures of structures of structures, and you keep actually organizing information in essentially what becomes like a tree. And that tree is branched in such a way that every level contains information, but there may be information below that level. And you may keep doing that over and over again throughout the process. So these are what are called structured arrays. Does it make any sense? Yeah? Now let's think about this in the context of something else, which is really useful. Think about what you would do if you had to store information. Let's suppose you're trying to compute the solution of a differential equation, and you want to compute that solution for some parameter that varies. Well, you could have the solution to each value of that parameter. Remember the problem I gave you on the first homework? I asked you to do this for e equals 0, 1/4, 1/2, and 3/4, right? You could have a structure element, or in other words, an element in this structured array, where you store the solution for that particular value of e. So in that case, your structure could be like solution, right? And solution of 1 could contain the following things. It could contain time, which would be a history of the time, which would be the entire grid of time points. It could contain position, which would be the first 3 components of what you would get when you integrate, when you get the state. Then it would contain the second 3 components, which you could call velocity, which would contain the velocity. And it could also contain the parameter that you're varying. You could have solution of 1.e equals. And then you could say, well, E was my parameter, so I'm going to call the first one E equals 0, and the next one E equals a quarter, the next one E equals a half. And we're going to actually go through and we're going to do this with that problem that I set up on, that I gave you for homework, so you can see how this actually works. But before we actually get there, this is how structures work. There's another construct which is also useful in the context of storing information, and it's what's called a cell array. All right, so I'm going to clear all the memory. Now it's a cell array, it's not celery. Okay, so you got to be careful. All right, so it's an array. All right, so what you do with a cell array is, I'm going to create one just to make it easier on everybody to see how this works. Cell array. Suppose I have a cell array that's 4. Let's say, I don't know, 5 by 3. Now you see that the cell array contains information that's stored. Now it is actually stored by index. But what's really cool about a cell array, which you cannot do with a numeric array, you just can't do it, is that each entry in the cell array can contain different kinds of information. So for example, I could say C, and now you have to be careful when you access a cell array, because you have to use curly braces to access a cell array. It's not a regular parentheses, it's actually a curly brace. So I can say C of 1 comma 1 is equal to, and I can put something in here. I can say 3 p.m. I'm just gonna put something just for the sake of putting something in there. So now you can see C of 1 comma 1 is 3 p.m. But I don't have to have all of these things be strings. You notice that that's a string. So I can say C of 1 comma 2 is equal to pi. And you notice that C of 1 comma 2 is a real number. It's pi, right? So if I look at the entries in the cell array now, if I actually just print the entire cell array and I say C, you see that this entry right here has a different type of data in it from this entry right here. The entry 1, 2 contains a real number. The entry 1, 1 contains a string. So I can actually organize information indexing into the array, and I can store different kinds of data in the different elements in the array. I don't have to store the same kind of data. This becomes very useful when you have information that's different in size, and you can actually do it in such a way that you can organize information this way instead of using a structure. So now going back to this example that we did in class, that we did on the homework, which I'm going to do in a little bit. I'm going to do it both ways. I'm going to do it with a structure, and I'm going to do it with a cell array. You could actually index the cell array in such a way that your index corresponds to the value of E, because you've got E equals 0, E equals a quarter, E equals a half, E equals 3/4. So you have 4 values of E. So you could do 1, 2, 3, 4 as being the values of E, and as long as you know that that's how you indexed it, you can create a cell array that contains the different information that has the trajectory. So you could have the first column be the values of the time grids for each one of the 4 values of E. The second column could contain the position for each of the 4 values of E. And the third column could contain the velocity for each of the 4 values of E. If you prefer to organize information that way instead of organizing information in a structure, that's perfectly fine. Just realize that when you do it, you're not going to have names. It's not going to be as much of a naming convention, whereas a structured array is based on names. A cell array is based on index and indices. And it gives you a way to be able to organize information in a really clean, structured way. So this now allows me to be able to show you how this actually works for this example that we have in this homework assignment. So I'm going to go and I'm going to pull out this homework assignment. We'll get. I want to go back to this problem. So let me find this file. Can everybody see that? Yep. Okay. All right. This is your homework assignment. All right. So let's go over to the page which has this problem. Now I'm not going to go through the whole problem, of course. What I am going to do is we're going to start with these differential equations, and I'm going to code them, and I'm going to use these initial conditions. Now you notice that in this problem, I had you set up a whole bunch of these initial conditions based on the value of E, and I said E is between 0 and 3/4, stepping by a quarter. So I have 4 different solutions that I need to set up. So let's actually go through and let's set this up. I mean, we're gonna go through the same process I went through before. So this is going to be 2-body. I'm going to call this 2-body polar. Now I'm going to open 2-body polar, and this function is the exact function that we have sitting in these differential equations here. And again, it depends on mu. So we're going to do function, and I'm going to say PV dot is equal to 2-body polar T PV, and now it's a function of mu. And so the differential equations here are R dot is equal to VR. I'll fill in all the gaps in just a minute. Theta dot is equal to, this is how I code things. By the way, just to let all of you know, I code backwards. So you're going to find that I do this a lot, where I code at the end, this is what I want. I want these differential equations. But I don't code forward by thinking about how I actually start with the information given and get to the end. I start at the end and I work my way backward to what it is that I need. And you'll see what I mean in just a minute when I do this. So I've got theta dot, and then I have VR dot is equal to, well, what does it say? It says V theta squared over R minus mu over R squared. And then I have V theta dot, and this is another thing you'll see me do a lot of, is I align my equal signs so that I can read things easily. V theta divided by R. Now, clearly I can't leave it this way because I don't have an output PV dot and I never use the input PV. So I need to now go backwards and figure out, well, what are these things? Well, R is equal to PV of 1. And I know theta is equal to PV of 2. And VR is PV of 3. And V theta is PV of 4. Now, that gets me from the beginning through to these differential equations, but now I need the output, right? So the output is PV dot is equal to R dot theta dot VR dot V theta dot. Now, I realize that a lot of you don't have as much experience as I do doing all this stuff, but understand that coding is, a lot of it is just logic. You have to work your way through the logic. You have to ask yourself, what do I know? What do I not know? How do I implement this thing? Then it becomes syntax, right? So it's logic and syntax. And I think some of you, and I've noticed this before, struggle with syntax too. And to be honest with you, you're not the only ones that struggle with syntax. I also struggle with syntax. I don't get it right every single time. I make mistakes. We all make mistakes when we code things. But if your logic is sound, you will be able to work your way through the syntax without too much trouble, because it is exactly what it is. It's a programming language, so there's syntax involved. All right. Now this is my function that computes the right-hand side of the dynamics. Now I'm going to create my function 2-body main. Now this is where all those cell arrays and structures come into play. So let's look and see what I need here. I need initial conditions. I need a whole bunch of things, right? Now I asked you to say mu is equal to 1, right? So that's the first thing I'm going to put in this code, is mu is equal to 1. Now once I have that, I need these initial conditions. Now you'll notice that in order to be able to code R0, theta 0, VR 0, and V theta 0, R0 was frozen at 1. That's what I asked you. I said just assume R0 is 1, right? And so we're gonna just keep it that way. So we're not actually going to change the value of R0, but we are going to change the value of these other things, these components here, VR0 and V theta 0. So I asked you down here for, let's see, where's it here? Here are the initial conditions right there, right? So I know that R0 is 1, so I can just set it right at the top of my file. So I'm just going to set it. The next thing is that I have theta 0. Well, theta 0 is 0. You're also going to find this somewhat painstaking on my part, because I do all these things just so I don't have to deal with them later. That's a lot of the reason I actually do this, is because I don't want to have to deal with this stuff later on and have to fix it. So I just try to do it as well as I can at the beginning, so that I can like make this easier on myself down the road. So it saves me time, and it does take me a little bit longer at the beginning to do it. But now v theta 0. Now you'll notice that v theta 0 is the thing that changes with the value of e, right? Because it's equal to the square root of mu times p divided by r0. But it's not, if I write square root of mu times p divided by r0, p depends upon this value e, right? So I need to know what p is, right? It's equal to r0 times 1 plus e, right? So if I work with this equation, I've got to figure out what p is, but p keeps changing, right? So what I'm going to do is I'm going to create a vector of e's. This is equal to 0, 1, 2, 3 divided by 4. So now I have all my values of e. So I know that this thing has to run for j equals 1 to the length of e vector. And now what am I doing? Well, every single time through this loop, I have to solve this thing for these values, for these initial conditions. The only one that changes is v theta 0. So that actually has to go inside the loop. The other ones don't have to go inside the loop because they're constant, so I can leave, they never change, so I can put them outside the loop. But now I have to compute p. P is equal to, well, it's equal to r0 times 1 plus e. But e is equal to e vector of j. It's the jth entry. I'm doing this on the jth run. So now, given that I have these, I have all this thing set up. Now, I could have made a mistake with something else, but at least syntactically, this is correct, right? So I can work with this information. Now I can set up my initial condition. So PV0 is equal to R0 theta 0, VR0, and V theta 0. Now you see that allows me to solve the problem for this particular run. So I can put the options outside here, just to I say options equals ODE set reltol 10 to the negative 10th, which is what I asked you to do. And then down here, I say T out, comma P out equals ODE 113, and then I say at two body polar with these initial conditions, and now I need a time span, and I have options, and I have mu, which is my parameter. So I got to figure out this time span, right? So I said the time span is equal to from 0 to 2 pi times the square root of a cubed over mu. So you notice that I need these values of RA and A in order to be able to compute that time span. So I'm going to go do that now, which is that RA is equal to R0, well, it's P divided by 1 minus E, sorry. P divided by 1 minus E. And then I have A. And A is equal to R0 plus RA divided by 2. So now I have the value of A. So now I can compute this value tau, which is my TF. So T0 is 0. TF is equal to 2 pi times the square root of A cubed over mu. So it's 2 pi times the square root of A cubed over mu. So now I have my time span, and just to make it easier on myself, I'm going to set this time span to linspace T0 TF, and I'll do 500 points. So now I have a time span. Now, assuming I don't have any syntax errors, which I could very well have syntax errors, this code should integrate that differential equation for all 4 values of E. Now, before I get into structures, let's just make sure that this thing actually runs. I have no idea whether it's going to run. So, if you're like me, I make mistakes. Yeah, it's not going to run. So, last entry in T-span must be different from the first entry. All right, so T0, because I did the syntax wrong. So this should be t-span. It's the order of the inputs. Now let's try it. Okay, it ran. Now you'll notice that when I'm done running this code, what's going to happen? What's in T out, P out? What do you think is in there? I just ran this code. Now this is where like you as the coder have to figure out, well, what is it that I just did? I just ran this thing in a loop. So what should the value of J be? So what do you think? What do you think the value of J is? Yeah, it's 4, because I ran the loop from 1 to 4, right? Ran it to 1 to the length of E vector, right? So what is sitting in this value, in this array, P out? Like T out is the time, but what is sitting in this array P out? So there's P out. So if I do a polar plot on P out, and I want to do theta versus R, then it's P out colon comma 2, P out colon comma 1, right? And if I do that polar plot, I get that ellipse. This is what all of you did on this homework assignment, right? So you got this ellipse. Now notice that ellipse is only the last solution. It's the one for E equals 0.75, right? Because J equals 4, the value of E that corresponds to J equals 4 is 0.75. So how would you store this information now in such a way that you can make it easy on yourself? Well, this is where a structure really helps, right? So what you do is you create a structure. Now you can do this a lot of different ways, but you can just say solution equals. Now the easiest thing to do is you can just say struct with an empty argument. So if you just say struct and you don't put anything in there, it gives you a structure with no fields. But what you can do is you can either do that or you can create it on the fly. But what I'm going to do here is I'm going to store in this structure solution, I'm going to say solution of 1 dot time is equal to T out. And sorry, not solution of 1, solution of J dot time. Solution of J dot position is equal to P out colon comma 1 colon 3. And then solution of J dot velocity is equal to P out 4 colon 6. Now I can also do the following, which is that I know that this thing depends on this parameter, right? So I can say solution, and in fact I'm going to put the parameter first, because the order in which you create the fields is the order in which they show up in the structure. So solution of J dot E is going to be E vector of J. Now look what happens when I run this now. So if I do this and I run this code, it's still going to run, but not going to run. Okay, so let's look here. Oh yeah, sorry. Yeah, I was thinking three dimensions. Sorry, thanks. 1, 2, 3, 4. Thanks for pointing that out. So let's try it again. Okay, now look at solution. You see it's a struct and solution of 1. Let's just look at the first one. See, it corresponds to E equaling 0 because I put it there, right? I put E as a field in my structure, and you see that I now can work with this in such a way that I have the hang on, my earbuds cut out again. Sorry. The structure for 1 corresponds to E equals 0. The structure for 2 corresponds to E equals 0.25. The structure for 3 is E equals 0.5, and the structure for 4 is E equals 0.75. Why does this help me? Well, it helps me because look what I can do down here. I can do this plot all at the end. I don't have to do the plot in the loop. In the loop, I'm confusing data that I'm actually doing computations on with plotting. Now I can decouple the plotting from the actual computations. I can do all the calculations, save it in a structure, and now I can plot it. Now look what I can do. I can say plot, and this admittedly is a little bit of a long code, but I'll do it just to show you how this works. So I can say solution of one dot, well actually you know what, let's say solution of one dot position. Now I know that theta is the second component of position, so I can do theta, actually, and this should be a polar plot, so hang on a second. So 1. Now I can do polar plot. Now what I can do is I can copy this and I can put it all in one plot. So that's the first one, right? A solution of 1 of 10, and then I can do solution of 2. And then I can do solution of 3. My mouse runs really slow when I'm trying to record, so that's why this is taking so long. And my keyboard too. Now, assuming I don't have any syntax errors here, let's do this again. And I can look at my figure, and you see all 4 solutions are on that plot now. You see what it does is it provides you a way to organize your code. And organize your thoughts at the same time. Doing computations is not the same thing as displaying the output of computations. They're separate processes, right? So when I'm plotting, I don't want to be concerned about the data, about how I got the data. I just want to plot the data. When I'm doing the computations, I'm not interested in what the plots look like because I haven't done the computations yet, right? So this way I can separate these two things into 2 parts. Now, if you don't like doing it that way, I can easily change this to be able to work with cell arrays. And in fact, I don't even have to do anything, and I can keep everything that I have in this code. So what I'm going to do is I'm going to create a cell array. So I'm going to call this sol cell. So this is a cell array, and it's going to be a cell array. Now, what's the size of the cell array going to be? Well, it depends on how I want to organize the information. But I know it's going to somehow have to be dependent upon the length of E vector. So it's going to have 4 rows. And then what I'm going to do is I'm going to make it 3 columns, just because I'm going to have time, position, and velocity. So now look what I can do. And I can do the same thing I did with this solution structure, except for I'm going to do it with a cell array. So I can say sol cell of, now I've got to be careful, it's j comma 1. This is equal to t out. And then for 2, that's the second column, that's going to equal p out of colon comma 1 colon 2. And then the third column is going to be 3 colon 4. Now, it's the same information, but it's organized in a different way. But there's a really cool thing you can do when you do this, and I haven't shown it to you yet, and I'm going to show it to you now. It is seriously neat. This is beautiful. Look at this array. You see what it contains now. It contains the time, which is a one-dimensional column vector, right? Just a column, it's not a matrix. But the position is 2-dimensional. So these are dissimilar sizes of data. So as a result, I can't easily stick it into a numeric array, but putting it into a cell array is really easy. Now look what happens when I do this. This is really fun. All right, I can do sol cell, and I can say 1 comma 1, right? But in the case of position, I know that sol cell of 1 comma 2 is actually the position corresponding to that value. But if without actually accessing each of these individually and having to generate entropy, I can do the following. This is actually how, and it's really beautiful. And when you look at it for the first time, you look at it and you say, that is weird. Like I would never think to do that. But here's what my polar plot would look like if I actually do this with the cell array. I can say sol cell, and I can say 1 comma 2. That's my position, right? For the first entry. And I can say colon comma 2, sol cell 1 comma 2 colon comma 1. I can literally do it all at once. Look, I'll do it over here. Sol cell 1 comma 2 colon comma 1. It says give me the entry into the cell array 1, 2, and give me the first column associated with that. And it gives me the first column. It's really nice, right? And then I can repeat this structure. You know, when I say structure now, I mean like I can repeat this approach over and over again for all 4 of these, right? I can do sol cell. Now, if you prefer to store information this way, it's perfectly fine. I can go 2, 2. Sometimes it's better to do it one way. Sometimes it's better to do it another way. But here I do 3, 2 because that's my third element, my third value of E. And then I can do 4, 2. Now, I didn't store the values of E, but I could have done that too, right? So now, if I grab this polar plot and I go over here and I close my figures, there you go. It's the same plot, right? But the information is stored differently now, right, than it was before. So you see that in the process of doing all this, we have created, it's a data management thing, right? It's not that you can't do it some other way. I'm not saying you can't do it some other way. I'm saying that there's a way to do it that makes it easier to understand what you're doing relative to what you would do if you were just putting your data anywhere and everywhere you feel like putting it. MATLAB provides you these really nice ways to organize information. Structures and cell arrays are the primary modes with which MATLAB has to be able to organize information. And one of the things that it does, and this is something that until you actually get into programming something, which you're going to be doing a lot of programming in this class, but until you actually get into programming things, one of the things you're not going to be completely in tune with is when you don't have to worry about the organization of data, your mind will focus more on the problem that you're trying to solve. And that is really important because in the end, right, you're doing engineering, you want to solve a problem. You clearly want to focus on the problem that you're interested in solving. You don't want to be focused on how am I organizing the data? It's so chaotic for me to organize data. Isn't there a better way to do this? Can I find a nicer way to organize data? Well, once you have a way of doing that, you can focus much more on your problem rather than focusing on all of these other things that interfere with your ability to actually get your problem solved. It's kind of like the same thing. It's like if somebody keeps bugging you when you're in the middle of trying to concentrate on something, you keep losing your train of thought, right? Well, if data management is something that's hard for you to do because you don't know how to do it or you don't have any experience doing it, you're constantly being distracted by the data management rather than solving the problem. And that is the key to all of this, is that you can now focus much more on your problem once you understand some of these constructs with data. You actually see that this code that I wrote, even with the cell arrays in here, this is it's not that much code, right? I mean, it's a pretty minimal amount of code. I mean, how much code do I actually have here? 30 lines, something like that. I mean, it's not a whole lot of code, but it's some code. I mean, it's not zero. It's just, let's see, I get to the end. Let's see, what does it say? 28 lines of code, right? And that includes all of the ways that I did this. Now, you could actually add a column to this cell array if you wanted to. I could make it 4 columns, and I could say the first column, instead of making it T out, I could just make it E. And then I could make sol cell j, 2 T out, and I could just shift all the indices by 1 so that the first column becomes my value of E. And then I have the same information organized again in a different way from the way I would have organized it had I done it with a structured array. That helpful? So, this is something that it will make more sense to you as you actually traverse the problems that you're solving, because you'll understand the reason to have to do it this way when you're actually spending the time solving a more complicated problem. When you're dealing with something relatively simple like this, you don't really necessarily see, oh, I could have done this without all that. I could have just done all the plots in the loop, right? That's what happens. But you don't want to be doing plots in your loops. I never do data analysis in the actual loop in which I'm doing the computations because it's very difficult to follow. I can't follow my own code. I need to decouple my code into different parts. And this gives me a way of being able to do that.